Okay, now let's define the symbolic reachability graph. Up to now, we know how to represent in a symbolic and unique way the marking classes, how to fire from a symbolic marking a symbolic instance in order to obtain a symbolic successor. So we have all the elements that are necessary to derive the symbolic reachability graph, and we'll see the algorithm. Okay. As you can see, the symbolic reachability graph construction algorithm is very similar to the reachability graph construction algorithm. So you start from a symmetric net, and you first have an initialization phase where the only marking that you know is the initial marking. So you will add, instead of adding the initial marking, you add the representative of its class, so the initial marking class, M0 hat. There is no arc, and that is the only symbolic state to be processed. Then we have a loop. So as before, this loop will examine all symbolic states as long as there are symbolic states to be processed. We pick one in the set of symbolic states, and we remove it from this set because we are going to handle it. And in this part, all the transitions are examined together with the symbolic firing mode. So the set of colors it can use for a symbolic firing. So if a transition can be fired from the symbolic state with its symbolic set of colors, giving a new state here, a new symbolic state, well, we add the new symbolic state to the graph, and we add the new symbolic state to the set of states to be processed, if it's a new one. If it was already existing, we don't add it. And we add also the arc here, corresponding to the firing, so from S hat to NS hat. The label is the transition together with the symbolic color set. So it's very similar to the construction of the reachability graph. You have to keep in mind that you don't manipulate normal markings and normal firings, but symbolic markings and symbolic firings. If we look at the results for the critical section access model, we can see that we have here we have the complete graph, which we didn't represent for the non-symbolic one. This symbolic graph has 7 classes instead of 20 markings. So you can see it's much smaller, and this is due to the fact that each symbolic marking represents a set of different markings, and each symbolic firing represents a set of different firings. The same applies to the dining philosopher's problem. You can see that initially you have a class of Z5 philosophers that are thinking. You have the 5 forks that are available. The only thing you can do is for one philosopher to take both of his forks. So a philosopher Z takes his 2 corresponding forks, and we obtain a new marking here in which 2 classes of philosophers are in thinking. One philosopher is eating, so the one that was chosen. There are forks remaining available, and there are 3 of them. And you noticed, so that was the example we had just before. We noticed that there are 3 philosophers in one of the classes that is represented in thinking, and 1 in the other one. Okay. And then from this marking, what you can do is put back the forks, and you go back to the previous initial marking you had, Or you can have the two firings that we have detailed for the firing rules that are represented here and that arrive in a similar marking. From this marking, well, the only thing you can do is put back the forks, and you have two possibilities, so either do it for Z1 or do it for Z4. And so the construction of the reachability graph is then finished, and we have 3 symbolic markings instead of 11. So it's much smaller. So what does the symbolic reachability graph preserve? Each marking is represented there by a class. So it's a symbolic marking that is reachable. Each reachable marking is represented by a class. Each firing sequence of the reachability graph is represented by firings in the symbolic reachability graph. And each sequence in the symbolic reachability graph corresponds to a sequence in the reachability graph. So these are very nice properties. However, we cannot distinguish between the following situations. So you have here 2 possible graphs. So imagine you have a net that gives you such a graph and a net that gives you such a second graph. I'll put it in different color. So the graph in yellow and the graph in blue, they both are represented by the same symbolic reachability graph, which is the one on the left-hand side. And you cannot distinguish between these two. That is, you cannot say from this from m hat here, well, you go to m hat prime here. You cannot say whether it is going from one marking to the next and back to the previous one, or going from one marking to another and then another and so on and so forth, as these all these markings are collapsed into the same symbolic marking, right? So far, the approach that has been presented imposes that all objects of the same class behave identically. A class group a set of objects that have exactly the same nature. The reachability graph obtained by reduction using these symbolic markings and symbolic firing rules is smaller, and the reduction that we obtain is maximal. But the question is, how can we deal with the case of objects that have the same nature but which have slightly different behaviors? So in the examples up to now, we've had objects that were similar and had exactly the same behavior in essence. For example, you could have a class that represents a set of processors divided into 2 subsets, fast processors and slow processors. And maybe they are all processors, so you would like them to be in the same set, to behave similarly, but you can imagine that the slow ones won't behave exactly the same as the fast ones. So to deal with this problem, we can use what is called static subclasses, and where each class is partitioned into a set of subclasses called cells, or static subclasses, where the objects within the same cell behave identically. So it's a further splitting of the classes. The symmetries of nets easily extends, as will be presented in the next sequence.